All right, thank you, Jason, and good afternoon, everyone. I'm Wei, and this is Alexei. We work for the Facebook storage hardware team, and actually our leader, Gordon Manning, is also here. All I want to say is, if you have any questions with the presentation with Facebook hardware, storage hardware in general, feel free to talk to us after this presentation. We have time; we can talk offline. So let's start. So I'm going to talk about how do we achieve deterministic I/O behavior on the Lightning platform. Before we start, so let's revisit the Facebook scale numbers, right? So Facebook today has 2.2 billion users on the main Facebook app. And then we also have 1.3 billion users on Messengers and also 800 million on Instagram. So to support this scale, we need to keep evolving. So as we add new users to our Facebook family, so we need to really scale up our applications and scale up our infrastructure. And this is, if you were at the keynote speech by Hans Jorgen yesterday, he was talking about we need to do the disaggregation of the resource so that we can keep up our demand. And disaggregation is really about getting the optimized compute, storage, and memory ratios. And if you see here, Lightning is our really the building block of a disaggregate flash effort. I'm sure a lot of you heard about Lightning. Facebook announced Lightning back in 2016 in the OCP World Summit back in San Jose. And we also provide an update on Lightning hardware development progress in 2017. And there we discussed a lot of the hardware challenges like hot plug issues that we have to solve. In this talk, I'm going to talk about how we actually deploy Lightning in one of the challenges we deploy Lightning in our production environment. And you can continue, you can really view this talk as a continuation of the Lightning series. And this is really how we address the challenges we face in our Flash deployment. Okay, so back to the slides again. So Lightning is a NVMe-based JBOF, just a bunch of Flash. It supports PCIe Gen 3 end-to-end connection. And it also supports SSD hot plug and support multiple form factors of the SSDs. And as I said, it enables Flash disaggregation at Facebook. Flash storage is really with Lightning decoupled from the compute nodes. So applications can share Flash storage at a flexible ratio. But this does not come. This comes with some impact on how we actually guarantee the QoS of the Flash applications, and this is really from main factors we have to look at this question, this problem. One is the characteristics of the Facebook Flash workload, and the other is really the intrinsic behavior of the SSD internals, like how they actually write the Flash, write the data to the Flash, and how actually serve the read IOs. And thirdly, there are also a divergence between our requirements of the Flash IOs and also the Flash industry trend. So if you don't do anything, the divergence is going to be bigger, as I showed you in the following slides. First, let's talk about the Flash workloads at Facebook. So we support multiple applications on our Flash platform. Mainly we run RocksDB, and we also run MyRocks, which is MySQL over RocksDB. And we also run some caching and indexing applications. So different applications, but they really have similar characteristic and or requirements on the I/O profile. So they are read intensive, and there are also with bursty writes. Read is normally like a 4K random I/O. Write is like a sequential bigger I/O size, like 128K. we also have strict requirements on read latencies, and especially read latency outliers. And the reason because is we want to guarantee every Facebook user have the same user experience. We also have multiple concurrent instances like database running on the Flash platform. Now back to the SSD, right? So if you look at the SSD internals, SSD, the source of read latency coming from several folds, right? There's read latency caused by collision with concurrent writes, and there are also Flash background operations like garbage collections, wire levelings, read scrub, block erase. These are the contributing the read latency. And also there's error corrections and error handlings, like those are delaying or prolong the read IOs. Now let's look at the Flash industry trend. And this is a chart basically to demonstrate the NAND die. NAND die is, for those of you like not that familiar with Flash, NAND die is really the building block of SSD, and it provides the minimum parallelism for the Flash IO access. And the NAND die, the size of NAND die is really doubling every 2 years. What this means is like to build a similar capacity point of the SSD, the number of dies you use is actually decreasing, which means the concurrencies on the SSDs is decreasing. And this translates to a higher, more undeterministic read IO because the number of dies is shrinking, and then it could be blocked by the write IO's concurrent writes. And there's also another factor here because NAND dies number of shrinking, and the throughput per terabytes is also decreasing. So these are the problems we face because of the industry trend on the Flash. And this is another chart to show you the divergence between the Flash capacity and also the CPU performance. So the black line is the Flash capacity growth over the years, and the yellow line is the CPU performance relative growth. The takeaway from this chart is, so you can see the CPU growth it's growing, but it's incremental, right? So it's the Flash capacity growth actually grows much faster than the CPU. So what this means is if you don't share the Flash resource across the multiple applications, our utilization of a Flash, because of the compute is not increasing, will continue to decrease. So we'll be basically stranding a lot of Flash in our system, and without because the CPU power is not there. And all of these are the factors that Facebook is is putting on this mission, like trying to dissect Flash in our production environment. Okay, so as I just said, we care about the read latencies, and because of the trends and because how internally SSDs operate, the read latency is going to get worse if you don't do anything, simply because we are sharing the Flash with Lightning. So our solution to this problem is called NVMe IO determinism. And this is Facebook lead the industry working with Flash vendors and also Flash customers to define a standard called IO determinism. And there's two parts of this standard. One is called NVMe Sets. This is about NVMe Sets and read recovery level. This is about partition the SSDs into multiple isolated entities so that we can guarantee the performance. And there's also another standard part of this IOD standard is called predictable latency mode, which Alexei is going to talk about. And this is to guarantee to give you almost like a read-only latency read-only I/O latency. So I'm going to talk about briefly on the NVMe Sets, and then Alexei will come up and talk about the PLM. So NVMe Sets. So the picture on the right is really about SSD. And what this shows you is there are NAND dies. The NVMe Sets is really an abstract allocation of SSD hardware resource, and each set has a dedicated NAND, as is showed here in each of the colored blocks. And also each set can have dedicated channels, flash channels. So each set can also carry with this. Each set can carry out its own writes and background operations. And they are physically isolated to avoid collisions by their noisy neighbors. The benefits of sets. So sets enables QoS regions at the SSD level. It has better support of multi-tenants on SSD. And the benefits of this is really, another benefit is really not that obvious, is the host software can leverage the sets as is. So because the sets are exported as a NVMe namespace, so the host software doesn't really need to change. And this is how we consider to use sets on Facebook environment on Lightning. So you can partition the SSDs into 4 sets, and you gave each set to a different application. And you can really, we can also support read the sets together to form a RAID with data protections, or you can give this whole RAID to application C. And this is a demonstration of the benefits of sets. This is the experiment we did back in our lab. It is a comparison between regular SSDs and the sets-enabled SSDs. The picture here shows, on the left shows a regular SSD. You can see even though it has 4 namespaces created, the backend storage, the NANDs are really mixed together. They're actually interfering each other in their I/O operations. While on the right is a sets-enabled SSD. So you create 4 namespaces, but the sets has dedicated NANDs and flash channels. The experiment we had is really about testing the noisy neighbor workload patterns. So what we did is we have one set running a target workload. Target workload means it's a 4K read-only workload. And also we have the rest of namespaces running as a noisy neighbor. And this is a chart about the results of silencing the noisy neighbor. What this shows you here, this is 2 kinds of workloads. One is the noisy neighbors of the four sets noisy neighbor, the 3 sets of noisy neighbor running random read and write at 4K. This is on the left. On the right is a read and write, random read and write, and with stream. So the takeaways from this slide is, by the way, the orange bar is the results from a regular SSD, and the blue bar is the result from the sets-enabled SSD, and these are on 4K random rates. So you can see with the noisy neighbor running, the improvements on a typical latency measure we measure is P of the 4/9 latency is almost like a 10x improvement. With that, this is about sets. I'll turn this over to Alexei to talk about the persistent, predictable latency mode.
Thank you. Hi, everybody. My name is Alexei. I'm a software engineer on the storage hardware team. And today I want to talk about a new approach for improving consistency of read latency that we developed at Facebook. There are many reasons why read latency can be inconsistent, but probably most often reason, and the one that's difficult to tackle, is internal operations that happens inside SSD. And there are three main reasons for that. First of all, there are much more internal traffic than external traffic. For typical data center grade SSD, there is a 7% extra capacity reserved for internal operations. And that means that in the worst case, one write can actually be converted to 14 internal writes, resulting in 14 times write amplification. Situation is better for enterprise-grade drive SSDs, but it's still significant. Also, these operations typically happen in batches because of nature of flash and efficiency concerns. And finally, it's very difficult for host to anticipate when these operations can happen. So it's like a black box to the host. So all this creates a perfect recipe for random latency spikes. And that's something that we want to address. We looked at several different approaches common in the industry, but I think it's important to understand how they work, to understand when they're applicable, what are the limitations. And probably the most common one is load limiting, like QDEPS limiting, bandwidth limiting. And it works by reducing queue wait time and probability of contention, by reducing variability. And it's worked quite well for reducing average latency, but effect on tail latency is not that significant. Also, there's a proven method of over-provisioning a drive, basically attempt to reduce write amplification by increasing the sector space available to flash translation layer. And it's proven to be efficient, but it's also expensive because this capacity is used internally and it's kind of wasted. Also, some SSD implement program erase suspend, and the idea is to reduce NAND wait times because the read operation is the lightest one, and programs and erases typically take much more time. And the idea is to break them into finer steps. Unfortunately, it's not that applicable in a data center environment because of constant load of reads. Also, there are open channel SSDs, and the idea is to bring significant portion of FTL to the host side, giving a lot of flexibility for application-specific optimizations. But it's kind of bringing a problem up the stack without explicitly addressing a latency problem. So it gives flexibility, but doesn't tell you how to improve your latency. And finally, there is new addition to the toolkit called NVMe Predictable Latency Mode. That's a new interface, new standard developed by Facebook with SSD industry leaders. And the idea is to segregate reads from all other operations, both internal and external, and in such way addressing all these effects of internal operations. And to do that, the idea behind PLM is to give host a limited control over scheduling of internal operations. So host decides when internal operations may happen, may not happen. It doesn't directly schedule them, which leaves enough freedom for SSD vendors to design their own algorithms, scheduling algorithms, and encapsulate all media-specific and technology details. But to make this work, drive needs to advertise some ramifications, like amount of time, number of reads and writes until next maintenance is required. So life cycle of PLM-capable SSD looks like this. It's basically a series of alternating windows of deterministic and non-deterministic modes. Basically, non-deterministic mode, it's like a regular SSD where when you can do reads and writes, all operations. And deterministic window is specific. So all this can be formulated as a contract between host and the drive, in which host agrees not to send reads and writes during the deterministic window and respect window characteristics advertised by the drive. And the drive agrees not to do anything unrelated to reads during the deterministic window. If this contract is broken because of exception or host misbehaving, a drive may switch back to non-deterministic mode. In that case, we lose latency advantage, but drive is still operational and data is still safe. So, like, it becomes normal SSD. And to test this, we developed a prototype. The idea was to leverage data redundancy of RAID 1 and PLM to segregate reads from writes and other operations. And we wanted to improve consistency of read latency and eventually achieve a read-only-like latency for mixed workloads. So what we did, we took MD RAID 1 and we stick a write cache in front of the drives. And those drives, they kept in different states. So most of the time they are in opposite states. One drive is handling reads, another drive is handling writes and doing garbage collection. But these states are not permanent. They keep changing. So each drive changes its state. That means that one drive is always lagging, and that's why we need cache to allow this drive to catch up later. To compare efficiency of this approach, we tried 3 different configurations. One is just one namespace, basically a single drive doing reads and writes. Also, we tried RAID 0, 50% over-provisioned, because it's comparable in cost to PLM. So we also utilized 2 drives. And finally, RAID 1 PLM. To make these configurations comparable, we make sure that capacity, usable capacity is the same, and we also limited read and write rate. We used a purely synthetic workload, random read for K at QDEPS 8, and a mix of random and sequential writes. And all block devices were preconditioned with 2 passes of mixed writes to make sure that garbage collection is happening inside SSD. So this is the results for the first 2 configurations. Red line is our baseline. It's a single drive doing reads and writes, and purple or blue line is a RAID 0, 50% over provision, and you can see that it's 2-time improvement for 6 nines. And this is significant for tail latency improvement. But single drive doing just reads, a green line, looks very different. So there's 22 times difference comparing to single drive doing reads and writes. Also notice that RAID 0 line is kind of similar to a baseline. It's choppy and it's growing, and it's different from a green one. So green one looks pretty much straight, and it's not growing that fast. And basically that tells us that when there is writes and erases, read latency is not very consistent. And finally, there is a PLM. So you can see why we didn't edit in the first picture, because it's almost completely covers a read-only workload. And keep in mind that these 3 lines are doing same workload, same performance, same capacity. And you can see how big is the difference for 6 lines. In reality, it's not completely read-only like. There's 10% difference based on our test. And we're quite happy with the results. So I want to add that RAID 1 is just a test vehicle that we use to validate this technology. Is not the only option to implement this. We are planning to look into other redundancy schemes like RAID 5, which can offer a better space utilization characteristics at the cost of write bandwidth. Also, there are different schemes, different ways to implement write cache. Some of them requires non-volatile memory. The ones that we used relied on NVMe metadata for headers and used normal RAM. Also, in our test, we used a single namespace from each drive, but it's possible to set up PLM to work with a single drive using several namespaces from the same drive. But to make this work, we need a new technical proposal that's being reviewed right now. It's called multi-set configurations. That's it. Thank you for your attention.
Thank you, Alexei. Thank you, Wei. Do we have any questions from the audience for the presenters? We have one over here.
You're saying that Lightning's aim is to disaggregate the SSD storage from the node at scaling.
Yep.
But you are limited on the number of PCIe lanes that the node can pump out to the Lightning sat underneath the node. So at the moment, I believe you're limited to 2 Lightnings per node.
There's 2 trays on Lightning, and each tray will connect to there are 2 trays for Lightning, and each tray will connect to a compute node.
Right. So a 2-to-1 scaling there.
It's on the tray basis, so the 2 trays are independent.
Oh, right. Yeah.
So they're not related to each other. So one tray is one height.
Okay. But my main point is that you're limited to the number of lanes provided by the node in terms of PCIe terms. Why have you not adopted NVMe OF to make you able to scale the number of Lightnings even more per node?
You mean the NVMe over Fabric on?
Yeah. So to replace the PCIe Connect with a Fabric Connect. Pardon?
The Lightning predates NVMe OF quite a bit.
Right. So my next question then is, are you turning the design of Lightning to make it NVMe OF compatible?
So our Lightning deployment, we're also running a network protocol on the front end to serve the block storage. We are not running at NVMe or Fabric at this point. In our case, it's always the network that's on the head node is the limitation, is the bandwidth limitation, is the bottleneck. It's not actually the PCIe lane at the back. So it's still the network side bottleneck. So with that regard, running a PCIe, running a generic block service or running a NVMe or Fabric, the bottleneck is at the same point. Yeah. Thank you.
All right, one more question over here.
What is the duration of the D state and ND state, and how deterministic are those values?
Typically, it depends on how much memory you have for write cache and what device is capable of. In our test, I think this state was about 5 to 10 seconds. It also depends on your write rate. So it's a combination of memory, RAM, or NVDIMMs that you have, and write rates that you anticipate. Because basically, this write cache is covering one drive for duration of the window.
All right, any other questions? One more?
Do you need a firmware upgrade if you want to test something like that? Or
Yes, you need a special firmware. It requires special firmware.
Are you also involved in the hardware design on the Lightning, concerning maybe different form factors from Flash? There was a presentation from Samsung about the NF1 form factor. Is that something that you're considering?
So the Lightning currently supports U.2 and M.2. With this generation, we are now thinking of Samsung's new form factors. So we're not supporting that. I mean, the form factor space is, there's a lot of options here. There's EDSFF and there's Samsung's proposal. So it really hasn't converged yet.
Any other questions? All right. Thank you very much, guys.
Thank you.
Thank you.